Assalamualaikum and hi, we are from Group 3. We'll be presenting about major losses in pipes.
So this is our team members, SYAFIQAH, NAJLAA and LAKSHMI.
When fluid flows through a pipe, it faces resistance, which leads to energy loss, mainly due to friction along the pipe. This loss is called major losses, and it happens because of the fluid's viscosity and the roughness of the pipe surface. Several factors also affect this loss, including the pipe's length, diameter, flow speed, fluid properties, and the pipe's roughness. To calculate these losses, we use friction factors, which can be determined using equations like Moody formula, Coolbrook or Blush's formula, or by referring to the Moody's chart. This method can help to determine whether the flow is laminar or turbulent. So, estimating head loss accurately is key to improving fluid flow efficiency. The objective is to determine the pipe friction factors, which is F, of different material, and the scope is the study involves different type of material, outer diameter and pipe thickness of pipe section, which are galvanized steel pipe, copper pipe 18 times 1, PVC pipe 20 times 1.5, PVC 20 times 16, and PVC 20 times 32.
Next is theory. Major losses are caused by change in friction, turbulence, and obstruction. We will use Bernoulli equation to calculate major losses. But before that, how do we know a fluid is tubular or not? We will calculate Reynolds number to find out. If the Reynolds number is between 4,000 to 500,000, then the fluid is tubular. From derivation of Bernoulli equation, we will get equation 1 and 2 to calculate pressure loss and major head loss. In order to determine the pipe friction, we will use the pipe roughness according to its material from table 1. Equation 3 is the formula to calculate the Reynolds number. By using Reynolds number and relative roughness, we can obtain value for friction factor from the Moody's chart. There are three ways to find friction factor. Either we take directly from the Moody's chart, or we use Blasius's formula or the Coolbrook formula. Blasius's formula is only valid for Reynolds number below or equals to 105. If we use Coolbrook formula, we have to use the iteration method to solve. This is the experimental setup for major losses in pipe test branch. How did we conduct the experiment? First, we connect feed and return hose to PVC 20 pipe section. Tube is connected to H1 and H2 and to the manometer. Pump are switched on. Gate valve is open to the maximum. Black cap is open to release all the bubbles before closing it back. Then, gate valve is closed completely. White valve is open until water level in H1 reach plus or minus 1 mm. The control valve is open slowly until water level in H1 reach maximum and H2 is minimum. The readings are recorded. The flow is reduced progressively by closing gate valve, and 5 different reading was recorded. Then manometer was transferred to gray box. The water flow was adjusted back as previous record to record the differential pressure. After finished, all the connected tube was taken out. Control valve and pump are closed. Step 1 to 12 was repeated again, but this time with different type of pipe section. After the experiment concludes, the setup is restored to its original state.
So these are the results that we obtained from the experiment. Table 8.3 showing the data for the galvanized steel pipe, Table 8.4 showing the data for the copper pipe, and Table 8.5 showing the data for PVC pipe with the outer diameter of 20 mm and thickness of 1.5 mm. So this table showing the data for other two pipes that we experimented, which is Table 8.6 showing the data for PVC pipe with the outer diameter of 16 mm and the thickness of 1.8 mm, while Table 8.7 showing the data for PVC pipe with the outer diameter of 32 mm with the thickness of 1.9 mm. So the first question in our discussion asks us to compare the coefficient of friction F for each of the tested pipe in our experiment with the coefficient of friction F from the Moody's chart and calculation using a formula of Blasius, Coolbrook, and Moody. And then we have to explain the possible reason from the differences in the value. Showing the sample calculation of the galvanized steel pipe, extracting the information given, and then the epsilon we get it from the constant table that we stated in the theory, finding the relative roughness, which is epsilon over the diameter, and then we're going to find the Q average, extracting out the temperature obtained from the experiment, and then we're going to calculate the velocity. After that, we're going to calculate the kinematic viscosity. While doing the interpolation, we got 6.9375 times 10 to the power of negative 7. After getting all the information, we're going to calculate the Reynolds number, which is we got 21677.28. Plotting it from the Moody's chart, the value of F, we get 0.042. And then we're going to calculate the value of F using all the formula. By substituting in the Blaster's formula, we're going to get F equal to 0.01121, while the Colebrook formula, we're going to get F equal to 0.04249. And then lastly, from the Moody's formula, we're going to obtain F is 0.005048.
From the table above, it can be seen that the values that we obtain from each formula are similar, while Moody formula give a value that are different from the three methods, which are Moody chart, Blushes formula, and Colebrook formula. The difference here is because 10 to the power of 6 is divided by the Reynolds number, give an impact to the calculation, but our Reynolds number does not exceed till 10 to the power of 6. Why there is the differences for each calculation is because the accuracy of the Moody formula is about plus minus 5% for smooth pipes, while for rough pipes it is about plus minus 10%. Blushes formula is also the simplest equation because it only involves Reynolds number, and it does not suitable for rough pipe because the equation does not have equivalent roughness of pipe, which is epsilon. Friction factor of galvanized steel is less accurate, and it is more suitable for smooth pipe such as copper and PVC pipe. Coefficient of frictions obtained from Colebrook formula and Moody's chart are slightly different, but it involve the same parameter, which are Reynolds number, epsilon, and internal diameter of pipe. And it is also suitable for both rough and smooth pipes. So the Colebrook formula and Moody's chart are more accurate because they consider pipe and water flow properties. However, the Colebrook is less practical since it requires iterative method, making it slower to calculate. The Moody's chart simplify by using the Colebrook formula to find friction factor for different pipe materials and display the results in a graph.
So for the second question in the discussion, asking us to rank the pipe and ascending trend based on the major head loss value obtained from the experiment, and we briefly have to explain the factors that influence the pipe ranking selection. So the equation for the major head loss is HL equal to FL over the diameter times with the velocity square over 2 times with the gravity. So we're showing the sample calculation for the galvanized steel pipe. We obtain 0.1996 meter, and then we calculated for each of the pipe. For copper pipe, we obtain 0.2878 meter. PVC 20 times 1.5 millimeter, we got 0.1937 meter. For PVC 16 times 1.8 millimeter, we obtain 0.1681 meter. PVC 32 times 1.9 millimeter, we obtain 0.0194 meter. So the head loss in pipe varies based on the factors like the diameter and the material roughness. The PVC 32 times 1.9 millimeter pipe has the lowest head loss because its larger diameter allows water to flow with a minimal resistance. As the diameter decreases, as seen in the PVC 16 times 1.8 millimeter pipe and PVC 20 times 1.5 millimeter pipe, the head loss increases due to the greater friction. When comparing different materials, the galvanized steel and copper pipe have the higher head loss than PVC pipes due to their rougher internal surface, which create more friction. Copper pipe, while smoother than the galvanized pipe, still contribute to the significant head loss compared to the PVC. Thus, larger and smoother pipe experience less head loss, whereas the smaller and rougher pipe face more resistance.
So the last question for the discussion is the factors that contributing to errors in the experimental data and the recommendation. So the first error is parallax error. So the recommendation is to ensure eyes are perpendicular to the scale of manometer. The second error is presence of air bubbles. So the recommendations is to slowly fill the manometer tube with fluid to avoid introducing air bubbles. And the last one is the connection of rubber tubes. So in order to avoid the error is to ensure the rubber tubes connecting the manometer tubes to the piping system are securely tightened to prevent leaks.
So these are the safety procedures for this experiment. The first one is to not touch the manometer glass to avoid air bubbles. And then the second one is to be sure that the eyes are perpendicular to the volume meter reading scale to get more accurate results. And the last one is to ensure the feeding and return hose are connected tightly to avoid leakage. In summary, the galvanized steel pipe exhibit the highest friction factor, followed by the PVC 16 times 1.8 millimeter pipe, and then the PVC 32 times 1.9 millimeter pipe, and then the PVC 20 times 1.5 millimeter pipe, and copper pipe. Conversely, copper pipe experiences the highest major head loss, followed by the galvanized pipe, and then the PVC 20 times 1.5 millimeter pipe, and then the PVC 16 times 1.8 millimeter pipe, and then lastly the PVC 32 times 1.9 millimeter pipe. Okay, so the result indicate that the major head loss decreases with a larger internal pipe diameter or lower fluid velocities, while longer pipelines lead to increased major head loss. To obtain more accurate value, Moody chart and kinematic viscosity table were utilized alongside various equations. However, several experimental errors affected the reliability of the finding, suggesting that specific recommendations are needed to improve the accuracy in the future experiment. So these are all the references that we use to get this experiment done. Thank you.